Hello, so welcome again. So as you can see on your screen, we have got the free CAD, uh, that is the KiCAD software, that is the open source, which can help us to design variety of electronic systems. And we can use the SPICE models in our designs to simulate the behavior of variety of circuits in a real time. That's what we have been doing since last few models. And in the previous model, we just saw how we use this circuit to design and simulate and analyze the behavior of Sallen-Key second order low pass active filter. So uh, we call it as a second order because the transfer function of this filter topology yields two poles in the complex S plane. And it's an active filter because we are using operation amplifier. And it is low pass because we have seen the behavior of it as a low pass characteristic. So now this time we have done a little bit modification. As you can see, instead of configuring this op-amp as a voltage follower or a voltage buffer, we have configured this operational amplifier as a non-inverting gain amplifier. So to the positive input, we have an input coming to the positive pin of the op-amp, but to the negative pin, we are providing voltage feedback through the resistors R3, and then there is this R4 from negative pin to the ground. The value of R3 and R4 are set to be 10K and 1K each respectively, so that the gain of this circuit is 1 plus R3 over R4. So the gain is like R3 over R4 is 10 plus 1, 11. So the gain, that is the ratio of VO over V4, which is V in, would be 11. And obviously, this whole circuit is acting as a filter, specifically the low pass filter. Now, there is this power supply, voltage supplies, which delivers the current to the circuit, and therefore they deliver power to the circuit. So it has been said to be plus minus 2.5 volts. So that's the dual power supply. We have got these VDD and VSS to the pin number 8 and pin number 4 of this op-amp, which are the positive and the negative supply pins to the op-amp. We have got this positive feedback right from output back to the positive pin through this capacitor, which is there. Then there is this capacitor C2 from the positive pin to the ground, and then there are these two resistors. So this specific arrangement makes it a Sallen-Key topology. To the positive pin, we are applying an external signal source that can have a DC value, time domain, peak to peak signal value, frequency, and AC magnitude if you want to perform the small signal analysis, for example, to obtain the frequency response. We have labeled this node as a V in, we have labeled this node as a VO, that is the output and the input respectively here. Now we have explained in previous module all these components, how we picked up them from the library here, how we added the SPICE model from the manufacturer, how we match the pins of the symbols of this device with that of the pins of the models of this device. That is a crucial point that we discussed, and in earlier modules we ran into a simulation error, then we troubleshoot, and then we solve that problem in the previous model. So refer to that if you are new. Now let us analyze the behavior of this filter, which is a Sallen-Key topology, a second order active low pass filter. And we will perform numerous analysis. So before that, let me click the electrical rule checker to check whether there are any warnings and errors. So warnings will ignore. There are these, but errors are 0. So again, I will click run ERC and check for errors. So errors are 0. Just don't care about warnings because they are like highlighted here because I have just copied and pasted this schematic from my earlier schematic. So there is a library warning about the libraries, but we can ignore safely. Close. Now you have to open the simulator and we'll see what kind of analysis we can do right over here. So here is like, let me open it again. Now we have opened the simulator and we are all set to understand it now. So I will click here, the new analysis tab. And the very first analysis I would like to do is to see the operating point in the circuit. So as soon as I do that, all the operating points in terms of voltages and currents will be highlighted on the schematic. So let me click OK. And now I have to click run simulation and look at this. This console window has got me the simulation. So what I'm going to do, I will just take it up. And now here, I would show you that right from the up. So we are running that temperature 27 degree, the simulation. X stands for the subcircuit and the V is the voltage of the components inside that subcircuit. These are voltages, then these are the current. Current from the source V1. V1 is our positive voltage supply of 2.5 volt. So that's the current. Then that's the current from the V5, another voltage source. That's the current through R2, resistor R2. That's the current through the capacitor. That's the current through resistor R1. Okay, similarly, these are the currents from the components inside the subcircuit indicated by X. Let me scroll it down a bit. We are interested in the total power consumption. Power consumption of XU1, that is the op-amp subcircuit, is 2.69 milliwatt. That's the power consumption. That's the power consumption of the resistor R4, that is 89 picowatt. That's the power consumption of R3. That's 899.9 picowatt. So you see that there is a 10 times because R3 is 10 times bigger than the R4. Okay, so that's the power of the components, and here is the power of your here is the power 2.6 milliwatt is the power of your op-amp that is consumed. So total power consumption you can calculate accordingly into the circuit, and then if you scroll it down, there is like voltage sources, voltages across the components, and here is the power consumption of resistor R1. That's the output voltage of 3.2 millivolt. So obviously DC voltage we have set it to 0. So there is no differential voltage of the op-amp between the pins of op-amp. So output ideally should be 0. However, there is a 3.2 millivolt, and that is an offset voltage, so output offset voltage. Here is the power consumption of R2, the power consumption of C1. That's the 2.5 volt VDD minus 2.5 volt VSS, and the power delivered by the source V5 is 1.3 milliwatt. So you can see that it's still a low power design. I have kept it in the power consumption of op-amp is like 2.5 milliwatt approximately. Now I will move to next analysis. Let's say I want to do the DC sweep analysis in case I want to see some behavior, some parameter is varying across the voltage and accordingly output will change. But before that, I will run the AC signal analysis. Okay, and the AC signal analysis means I will have the Bode plot. So number of points, let's say 1000 start frequency is 1 hertz, stop frequency, let's say 100 megahertz, and I will say click OK. Once that is done, let me minimize this window so that I can see the plot in a better way. So now you see that, but before that, let me show you on the schematic. This is the result of after running the operating point analysis. You see the voltages of and the currents in the red and the voltages in the deep red or brown are highlighted after the OP analysis. And that's the currents, and the current multiplied by voltages are the power. Here is the output current available at the output pin, that is about 300 nanoampere. That's the voltage at the output node, that is about 3.3 millivolt. Even though we don't have any differential input, we still have output of 3 millivolt. That's the output offset voltage. You can confirm that from the data sheet of this TLV9062. There is at this node you have a 300 microvolt. Then there is this current through R4, 300 nano, here 300 nano. There are like currents into the positive and the negative pin of the op amp. They are called as the bias currents. So that's about like 500 femto and 51 femto, 550 femto ampere, something like that. There is a zero current in the feedback through the feedback capacitor. There is a zero current through this capacitor. There is a current through R1 and R2 about minus 500 femtoamp. The current of this voltage source is minus 500 femtoamp. There's a voltage here, it's 0 volt, because we see here DC voltage is set to 0. Okay, so that's the result about operating point analysis. But now we have run the AC analysis. So we have set the AC equal to 1 here. And because of that, we are able to run the AC analysis. Now, what we are interested in, we have got the label of VO. So we will see how the magnitude of the output voltage VO varies with respect to frequency, and the phase of the output signal varies with frequency. So again, come back here and signals are available here. So before that, let me hit run. And after that, I will see plot V of VO. So now you see I have got a gain of about 21 dBV, and that is if you compare this plot with the plot we obtained in our previous module, the gain was 0 dBV, because we in that module we use the op amp as a voltage follower or voltage buffer. We don't have a gain, but now this time on your screen we have op amp configured as a non-inverting amplifier. We are using amplifier, and we are also therefore creating a filter circuit. So it's a low pass filter response of about, you have got the dominant pole at about 200 hertz, quite at a quite low frequency. You can simply vary that also, because you have increased the gain, so your bandwidth is reduced, obviously. So from here to this point, about 200 hertz, you have got the pass band, and after that gain starts dropping at the rate of minus 40 dB per decade. And then here you have a stop band of about minus 45. In fact, at this point, this is a cutoff frequency at this point where your this frequency point separates your pass band and the stop band. How about the phase? So you can look, the phase is also right here. If you see that it is 0 on the right y-axis and it stays 0, but from here at about 10 hertz or 20 hertz, it starts increasing, and total phase shift is about 135. At this one, at the cutoff frequency, you can see the phase is about 40 for 50 degree. So this is how you see that you have got this one, right? You can change the color if you want of this signal. Okay, that's how you can do that. Is there anything we can do or modify here? So what if you actually want to tune this gain, and accordingly you can see if there is a difference in the filter response. So what you do is before that, you can click also here, show spice net list. So this is your spice net list, and you can save it and call it in any other software or even ngSpice. So, but close it now. Then here you have like add, edit, or delete user defined signals. You can add from here, and for example now, but now here you can just add tuned value, select a value to be tuned. So I click here, I will select any one component so that I can tune in the value. So for example, if I select this 10K, let's say 10K, and then I go back to my simulator here. So here you see in the bottom here, I clearly see there is a maximum value of this register is 20K, and minimum I can go 5K. So right now I have the results for 10K. So what about I choose it 5K and look at that. The gain got reduced from 20 to 16, 21 to 16, but now bandwidth is scaled to like 600 hertz. Earlier it was 200 hertz here, but little bit scale up, and accordingly phase variation is also there. How about I do it 20K, but look at this now. You have got very high gain about 26, but your bandwidth scaled down to about just close to 100 hertz. So accordingly you can vary. How about you do one more thing, and you just let's say tuned value, you want to change this capacitor. So you click there, and again you come back to your tuned capacitor C2. So you just have it like 550 pico and see how the response varies, or if you take it 2.2 nano and see the response varies. But I think there is not much difference between what you can see here with the change in the capacitor. How about you delete this value of capacitor, rather you go to schematic again and choose this guy. So if you choose that capacitor, which is C1, and start tuning it, and let us see, you can make a little bit difference. So let's say you scale it to 4.4 nano. Yeah, there is some change here. You see now the bandwidth is affected, the gain remains stable because gain is set by the ratio of R3 and R4, no capacitance. Okay, capacitance is just changing your bandwidth pole frequency. So you can have that, you see that. Okay. So now let us set it to 1.1 nano. So here you got little bit extra bandwidth here. So this is how you can have your AC analysis done. So what I'll do, I'll just save this export current plot to the let's say some folder, let's say call it AC, and just save it. That's it. So you saved it. Then next time it's time to run some other analysis. For example, let us click here, and maybe I want to run now transient analysis, transient simulation. So I will apply a sinusoidal signal. So let's say time step is like 10 micron, or let's say 0.1 micron. I want very finer step. Final time is, let's say 10 milliseconds, or let's say 5 milliseconds. Initial time I can ignore because it is optional, otherwise default is 0. Click OK. So that is done. Now let me show you on the schematic. Here I have used the sinusoidal signal source, which has a peak value of 100 millivolt and the frequency of 1000 hertz. So 1 kilohertz. So I will see how whether this signal frequency is sufficiently passed by the filter. But from the AC simulation, we just saw the cutoff frequency was about 200 hertz, and now we are using 1000 hertz here. So gain will be reduced. As you can recall here, the plot, you have a good gain here, about 25, 27 dB, but the cutoff frequency is like 300 hertz. And now input signal frequency is 1 kilohertz. So obviously your signal will be reduced as compared to input. So we would want to verify that if we run that. So let's say click run, and it is running the simulation. And I have used a very finer steps. That's why this simulation will take a little bit of time. So it is like I have run the simulation for 5 milliseconds. So it is now 3 millisecond, 4 millisecond is coming right here, reference value. And hopefully, yeah, it stopped. So number of data rows we got about like more than 50,000. So what I'm interested in, I am first interested in seeing my input signal V of V in. So I will see that I have got 0 to 100 millivolt peak signal of input. Its frequency is 1 kilohertz. I can verify that with the cursor here. So let's say I click here, and I want to position those cursors from, let's say, the first valley point to the second valley point. So this point and this point. So I see here The voltage here is close to 100 millivolt. The voltage of the second cousin is 100 millivolt. Obviously, the difference between the two voltages is zero, ideally, but it's little bit difference. It's micro. But what about time? Is like 1.76, 2.73. So total difference, time difference is about close to 1 millisecond. So reciprocal of this time 1 millisecond is 1 kilohertz. So what we expected and what we applied. So output, you see now, instead of passing that signal, your operational amplifier got saturated. So op-amp is not really filtering this signal, rather it got saturated to the maximum supply voltages at either end, that is 2.5 and minus 2.5. So we have to be careful uh, about our values. How? Because we have chosen this to be 20K. So how about we vary it? Let's say I want to keep it like 10K. So there are a lot of options, and see if then there is some change in the signal. No, I still have that saturation. Even though I tune the value of a resistor, I have got the saturation there. So it is because I have okay, that's it. Let me tune this value also. Let's say I want to use it like 2 nano. Let's say close to 2 nano, what was before, and see. But this is not going to affect my time domain response, because the gain I have set is clearly there. So what I need to do is based on the AC analysis, what we saw, I need to change some the input signal parameters. Okay. So what I'll do, meanwhile, this simulation is being plotted, the data is being plotted. I will go back to schematic and try to change the frequency here. So I want to do like, instead of 1,000 hertz, let me choose it 100 hertz and save it, and then go back again to schematic and let me run the simulation again and see if there is some difference. There is absolutely no difference, because my operational amplifier is getting saturated here. Okay. So now it's time to troubleshoot. We have to find the answer. So before that, what I'll do, I'll close this. I will close this. I will just edit the simulation settings. Instead of 100 nano, I will say just do it like 1 micro. 1 micron step is okay. Okay, and then I will say like, not really. I will say run simulation. So it will be a bit faster. Look at this, the simulation got a bit faster. And now instead of yeah, so I have got only half cycle. So I will do one thing here. So instead of 5 millisecond, I will say like let's say 10 millisecond maybe. So check it and see how it behaves if I get the signals there. But my operational amplifier is getting saturated for sure. So I've got one cycle. You see this positive half, and then there is this negative half. But my operational amplifier got saturated. So this is the real. So when you design actually your circuit, this is the kind of concern you have. So let us troubleshoot this now. Right. So in order to find a solution or troubleshooting, what I have done is like set the frequency to 500 hertz or even lesser. Um, let's say I click here. This is the probing, and with the probing, do I get no? There is nothing I hear. So let me show you again. What I have done is click here, and I know that the pole frequency was about 200 hertz, so I set it to 200 hertz. That's the maximum frequency I can apply. And after that, values of R3 and R4 are set to be 1K each. So the total gain in the circuit is 1 plus R3 over R4, that is 2. So 20 log 2 will be about 6 or 7 dBV. So we'll see how this circuit will behave. And I'm going to tune the value of R3 actually, or I can tune the value of R4 as well. So there will be a gain bandwidth trade-off here. So here is a time domain simulation. I can choose the value of R3 and R4. Currently it is 500 ohm, not really 500. So I have to set it like about, let's say a 1K. If I choose it like 1K, then we'll see. Okay, so that is done. Run the simulation. So now look at this. I have got the red is my input, which is like 0 to 100 millivolt, and the output is like 200 millivolts. So obviously the gain of 2, right? So output will be 2 times bigger than this. But what is this? There is little bit distortion in the output signal. And obviously I have the output and inputs in phase with each other because it's a non-inverting amplifier. But this distortion is coming there. Look at, let's find the answer in the AC analysis for these values. So if I have already done the AC analysis, I'll click here and run the simulation. Oh, I have got this resonant peak, or there is this oscillation at frequency about 10 kilohertz. Right click and fit on the screen. But from DC to about 2 kilohertz, I have a constant gain of about 7 dBV, which is a gain of 2. The magnitude is 2, and the phase is also 0 degree exactly. But now I have got this ringing or oscillation at like 10 kilohertz. But why then is the distortion coming here? So this is the practicalities a designer has to take into account. So what I'll do, I'll increase the value and see. Let's say I take it to 2K. I increase the gain and again run the time domain simulation to see how the output behaves. Look at this. Output got saturated to plus minus 2.5 volts. So this is what I don't want. Same thing can happen with the AC analysis. Let the time domain be over, and then I will run the AC plot again to see how the response is likely to change. So this time domain is getting completed. Okay, it's done. How about AC analysis? Click here and look at this. The AC analysis seems fine, but in time domain, I don't have a ringing here in the Bode plot. So gain is constant up to the frequency of like 2, 3, 4 kilohertz, which looks fine. But time domain simulation, I got this problem here. So I got my operational amplifier saturated. That is because the differential input is too large and the gain is too large. So what I can do is maybe try to tune this value of the resistor. And what I'll do is go back again, delete this guy, and let's say I will click here at tune value and select the R4 there. So once I select the R4, I will come back to this screen, and now I have R4. So initially I can set it to 500. So the gain is now increased, and we'll see how the time domain will behave. Again, it got saturated. I don't want to wait for full simulation. I'll stop it. How about I make it like close to 1K or just less than 1K. So the gain will be like close to 2. And look at this. I have got this earlier waveform, but now R4 is close to 1K, R3 is 1K, so the gain is 2. But how about I do it like little bit less again? The gain is increasing, but the output is getting saturated there. So that's the problem here. That's the problem here. How about I increase it little bit? Now it is getting fine and it's perfect. So the value is like, let's say close to 1.5K, the R4. But now the R4 is bigger than the R3. R3 is 1K, R4 is 1.5K. So 1 divided by 1.5K. You can set that value, no problem. So it's like 1 divided by 1.5K. So you can choose that gain is about 0.7 plus 1. So 1.7 or something will be your gain. Okay. Otherwise, you can choose to play with some other values, play with the bandwidth, with the capacitor change, or maybe this two resistor change, something like that. Or maybe, and then change the bandwidth and then change the frequency and something like that. Okay. So you can easily see you are able to pass this frequency of 200 hertz with the gain set. What about its AC response? Click again and see there is a ringing here, but up to this frequency, 1 kilohertz, you have a good response of and gain of 4 dBV. Fine. So now what about I increase the frequency? Let's say instead of 200, I want to make it like 500. Let's say 500. Click OK. I will go back to simulation, click the AC analysis. So this is correct. How about time simulation? Click it and see. If I double the frequency, will that frequency signal be passed? Yes, it's sufficient. The time domain signals are pretty good. So this is how you can tune in your circuit, export current plot to the as a PNG, save it something like that, save it somewhere. That's it. That's it. So this is how you got your time domain simulation ready. How about you perform the FFT of this signal? Click the new analysis, select I want to do FFT. I want to have the FFT of both input and output. Click OK. Click output FFT. Oh no, I have to first run here and then click here. Very good. So I've got two peaks, one here, one here. And I've got this also. For the input, there is no second peak here, but for the output, I have got this. This is like some other frequency component there. Okay. So this is how you can choose to tune in your circuits and all that. So I hope you found this design of Sallen-Key low pass filter useful, and you can also now play with the tuning of the component values. With this, wish you happy learning. Stay tuned for more informative content like this and share it for the wider reach.